Good morning everyone, we are from Group 9. Today we are going to present our topic entitled Arithmetic and Geometric Sequence, Terminal Expressions of a Piston Route. Before we begin, let me introduce my team members. I am Nur Aisyah Najihah binti Asif, AA251251, and I am joined by Nur Rabiatul Adawiyah binti Othman, AA250580, Nur Alisha Balkis binti Selamat, AA251706. Ainur Madiha binti Muhammad Nur Hasni, AA250307. And the last is Nur Najihah Izzati binti Muhammad Iskandar, AA251696. My name is Nur Aisyah Najihah binti Masif, number metric AA251251. This project studies the problem of terminal expansions of Python routes in internal combustion engines. During the engine's operation cycle, the Python route will experience repeated by heated and cooling, which cause it to expand and contract. Over time, heat and material fatigues cause the route to elongate permanently. The main problem studies is how we can module the expansions this piston route using arithmetic sequence, linear expansion, and geometric sequence, proportional expansions. This is critical to identify at what circle the leg of the road will accept the maximum safety limit M, because road fails can cause severe damage to the interior engine.
My name is Nur Najihah Izzati binti Muhammad Iskandar. My nomenclature is AA251696. Alright, for station 1.1, filler table. This table is used to identify and organize important information related to the problem study in our PBL project, which was focused on thermal expansion of a piston rod using arithmetic and geometric square model. First, under the facts section, we identify several key facts. The piston rod expect a contraction rate of the heating and cooling during site. The entire length of a piston is a A1041 mm, which a constant is 0.4 mm, a geometric rod of R 1.004, and a maximum safe limit of M 110.0 mm. If head length of the piston rod is set, the value sinusoidal failure may also. In addition, material failure can expression the expression in the geometric model. Next, in the ideal section, we proceed to measure above the first approach and arithmetic square to calculate expansion based on the calculation increase a leg. This discussion above applies a geometric square which considers proportional growth to a 5 ratio. Both models are compared to determine which on pressure unsafe condition or like this compression also help to understand heat and temperature affect the material of over time. For the linear issue section, several questions need to be addressed that include determining the formula for the nth term and sum of the 4-point square. Identify the scale which the piston rate exceed the safe limit of 110.0 mm, like how to use Microsoft Excel. To conclusion, a table for 20 side and geometry calculation graph and understand how temperature a material property influence the material result. Finally, under the action plan section, or the group plan to refer to Algebra textbook and lecture notes to trip the regular formula. Manual calculate will be performed to determine the volume of and with a piston rod which of safe limit. Microsoft Excel will be used to generate table and professional card. We will also refer online research and engineering material to better understand the scientific principle behind the thermal expansion of the piston rod. In conclusion, the filler table help our group clear understand the problem in a structured manner and serves as a key guide in conclusion the analysis and session for the PBL project.
Is Nur Alisha Balkis binti Selamat. My matrix number is AA251706. So for part A, arithmetic sequence, we use general formula. To calculate the arithmetic sequence, we use the following formula. Formula for the n term is Tn equal to a plus n minus 1 multiplied d. For the sum of the first n term, which is Sn equal to n over 2 multiplied 2a plus n minus 1 multiplied d. Given the value is a equal to 104, d equal to 0.4 and m is 110. 2.1 Roman extension at cycles 15. T15 equal to 104 plus 15 minus 1 multiply 0.4. We got the answer is 109.6 mm. Roman total extension after 15 cycles. S15 equal to 15 over 2 multiply 104 plus 15 minus 1 multiply to 0.4. We got the answer is 1602 mm. 3 Roman is average extension per circle up to 15 cycles. So average equal to 1602 mm over 15 equal to 106.8 mm. For Romans, determine the first cycle and when Tn greater than 2 equal m. A plus n minus 1 multiply d greater than n equal to m. 104 plus n minus 1 multiply 0.4 greater than n equal to 110. N minus 1 multiply 0.4 greater than n equal to 110 minus 104. N minus 1 multiply 0.4 greater than n equal to 6. N minus 1 greater than n equal to 6 over 0.4. N minus 1 greater than n equal to 15. This means n is 16 to extension reach the target value at cycles 16. Next part B, geometric sequence. We use general formula to calculate the geometric sequence. We use the following formula, which is the formula for the n term is Tn equal ar power n minus 1. For the sum of the first n term is Sn equal a multiply 1 minus r power n over 1 minus r. Given the values a equal 104, r equal 1.005 and m is 110. 2 1 Roman extension at cycle 15. T15 equal 104 multiply 1.004 power by 15 minus 1 9.98 mm. 2 Roman total extension after 15 cycle. S15 equal to 104 multiply 1 minus 1.004 power by 15 over 1 minus 1.004 equal to 1604.445 mm. 3 Roman average extension per cycle up to 15 cycle. Average equal to 1604.45 mm over 15. The average is 106.96 mm. 4 Roman determine the first cycle when Tn greater than to equal m. Ar power n minus 1 greater than n equal to m. 104 multiply 1.004 power n minus 1 greater than n equal to 110. 1.004 power n minus 1 greater than n equal to 1.058. N minus 1 ln 1.004 greater than n equal to ln 1.058. N minus 1 greater than n equal to 14.12. N greater than n equal to 15.12. The extension reach the target value at cycle 16. First, enter the 20 cycle data that you have calculated for Tn and Sn, then following by n and m. Select data Tn, n, then press insert You have to choose graph. Repeat the same step for geometry and comparison.
My name is Nur Rabiatul Adwiyah binti Osman with the matrix number AA250580. So for this program-based learning project, which is the video presentation, I am going to talk about the discussion. I am going to talk about the discussion. So we have found out through a comparative analysis by using Excel-based modeling, our team has found out that the geometric model is a much more superior tool for predicting when will the piston rod eventually reaches its maximum safe length level, which is at 110 millimeters. Why do we say so? Because while the arithmetic models predict that the failure will reaches at exactly cycle 16, because it is based on a fixed linear expansion from uniform heating on the arithmetic models. But the geometric model managed to identify the onset of danger at cycle 15.12. Well, this is only a small differences, but it has a big effect. So, because the rod operates in a discrete cycle, we cannot accept the 15.12. But this decimal indicates that the materials become unsafe shortly or almost immediately after 15th cycle begins. So this provides a much more conservative and a much more safer window for maintenance than the linear approach does, which is the arithmetic models. So this accelerated growth is scientifically grounded in the behavior of atomic vibrations. So because as temperature rises, atoms within the aluminum alloy vibrate more intensely, causing the dimensions to expand proportionally in all of directions, including both the length and diameter, rather than at a constant fixed rate. So, this proportional expansion, often driven by material fatigue, proves to be a far more extreme than a simple linear expansion that caused by uniform heating alone. But furthermore, the results are heavily influenced by material selection, which is this could be one of the factors, or could be the factors that influence the result. One of them would be material selection, because while standard aluminum alloys are designed for high thermal stress, prolonged engine uses maintains a constant high temperature that compounds the rate of proportional change. This is also what we included operational duration into one of the factors that may influence the result. So consequently, the team concludes that the geometric model is the most reliable method for identifying early stage failure and also preventing catastrophic engine damage, as it more accurately reflects the physical realities of thermodynamics and also material degradation. So, thank you.
Hello, my name is Ainur Madiha binti Muhammad Hasni with number matrix AA250307. I'll be wrapping up our presentation by looking at what our results actually mean for the engine. To recap, our team analyzed Group 9's data, starting with an initial road length of 104.0 mm. We test two different ways heat might make the road expand. In the first model, the arithmetic one, the road grew by 0.4 mm every single cycle. In the second model, the geometric one, it grew by a fixed percentage of 0.004. What's interesting is that even though the model works differently, they both hit the maximum safe limit of 110.0 mm at almost the exact same time during the 16th cycle. However, the geometric model shows us that as material fatigue sets in, the expansion starts to pick up speed. This is a big deal in engineering because it shows that expansion isn't always a slow, steady process. It can accelerate. This project taught us that math is a huge part of engine safety. Instead of just guessing when a part might break, we use algebra to predict it exactly. By understanding these sequences, engineering can schedule maintenance before a piston rod fails and ruins the whole engine. It really shows us that formulas like these aren't just for textbooks. There are tools to solve real science problems.